Hello, welcome everyone. My name is Farid Char. I am one of the tourist guides of Paraná Observatory, and I will be in charge of this virtual guide tour in ESO's La Silla Observatory. I am not alone, I am with the producer, Hector Salas. So, how are you, Hector?
Hi Farid, happy to be here once again. So my name is Hector Salas. I'm a PhD student at the Leibniz Institute for Astrophysics in Potsdam in Germany. I work mostly with topics related to the circumgalactic medium, so that's the environment of surrounding galaxies. And I have been a member of the team of guys for Paraná Observatory since 2019. I started when I was doing my master's at University of Antofagasta. And as Farid mentioned, I'm going to be the producer today, so I'll be switching the videos and pictures. But I will also be reading all your comments and questions, so please send us any question you want us to answer, and we will give a couple of instances to do it during the tour.
Okay, thank you very much, Hector. So yeah, you can send your questions or comments during this streaming, and we are going to answer later. Okay. So in the next hour, we are going to visit the region of Coquimbo in northern Chile. So we will virtually visit La Isos La Silla Observatory at 2,400 meters above sea level. So we are going to start the tour right now, and we are going to understand a little bit about the observatory. So we have a screen to explain a little bit about the organization, right? Yeah. Okay. Thank you. So we have a list of countries there. Okay. So ESO is an intergovernmental organization. Okay, and in this list we can see the ESO member states. We have 16 member states. The host, the headquarters, is located in Germany. Okay, and Chile is participating as the host state, and is the home of all observatories of ESO. Okay, so we are going to understand a little bit what happens in this observatory in the Atacama Desert. Okay, so we are going to do a simulation of a trip from Europe, in this case, to the Atacama Desert. So we are going to watch an animation to show you this journey from Europe to the Atacama Desert. And we are starting this journey in Europe, as I told you already, because ESO is an European organization. So in this map, outlined in white, we can see the European countries. And now we are going to move slowly to the Atacama Desert. So in this journey to the Atacama Desert, I want to mention that the mission of ESO is to design, build, and operate astronomical observatories. And what for? To enable important scientific discoveries and incentivize the promotion and cooperation in the astronomy field. So in this case, ESO it was started some site explorations in the 60s, and they did choose one of the best places on the planet to do astronomy, professional astronomy. This is the Atacama Desert in Chile. So around the 60s, Chile started a campaign of explorations of sites to attract international observatories such as ESO to our country. So Chile offered its territory, and ESO did choose the area that seems best. Okay, so now we are in the Atacama Desert in this animation. Now we can see the La Silla Observatory. The name of La Silla is because the mountaintop looks like a horse saddle. Okay, So now we are going to take a look at the different telescopes in La Silla. So we are going to show you something like a drone flight around this place. So you can see the different telescopes of La Silla. La Silla is located at 2,400 meters above sea level. Okay, La Silla was inaugurated in 1969, and right now we have 10 telescopes working there. Okay, 2 of them are operated directly by ESO. The most important and biggest telescope in La Silla is the 3.6 meter telescope in the top. Okay, in this animation, we can see the 3.6 meter telescope at the end of this journey. Okay? So this telescope was the first one to be inaugurated, and one of the main advantages of this telescope is that the main instrument is specialized in the discovery of exoplanets. Okay, so we are going to change the view because I want to share with you now about a 360 view of La Silla. Okay, so in this 360 degrees view, we can see the different telescopes here. These are the same telescopes that we saw before in the drone animation. And this one is the 3.6 meter telescope, okay, or 360, okay, because, well, 360 centimeters. Okay? So at the left here, we have the NTT. This is the New Technology Telescope. This is another important telescope in La Silla because of the technology involved. So we are going to visit the 3.6 meter first, and then we are going to visit the New Technology Telescope. Okay, so we are going to access right now, and here we are. So here we are at the interior of the 3.6 meter telescope. Okay, so this name, as I told you, is a reference to the diameter of this mirror, 3.6 meters. In this, let's say that in the 1970s, this one of the this one was one of the biggest telescopes on Earth. Okay, and right now at this moment, we have a special instrument inside. It's an exoplanet hunter. The name of this instrument is HARPS. This is a highly specialized instrument to search for other planets orbiting other stars, okay, outside of our solar system. So what we can see inside of this dome, well, of course, it's a giant dome. Okay, we can see the dimensions, the size of this big facility. Let's say that from the first floor to the dome, we have 25 meters. And all this telescope structure equals to a 7-story building. So everything looks small from here in comparison with the telescope. So for example, maybe you can see a person in this picture, okay? The person is here. So we are going to do a close-up, and you can see a person, okay? So this is a useful reference to understand the size of the telescope if we compare the telescope with the rest of the structure. So we are going to understand better the main components of this telescope. So I am going to open a picture in order to explain that. So in this picture, next to the telescope, we have three important things. First, in dark blue here, we have the structure holding the telescope. This structure is called the mounting. Okay, so this mounting is like a big arm to hold the telescope and to contain all the systems, the energy systems, okay, like the electricity systems. Now, on this arm, and parallel to the Earth's rotation axis, the telescope moves to follow the objects in the sky during the observation. Now, if we go up in the lighter blue, we have the telescope's body, okay? So in this structure, we have the main mirror, the primary mirror of 3.6 meters or 360 centimeters. And we have also the secondary mirror. Now, where is the main mirror? Where is the primary mirror? Well, the primary mirror is not visible here because it's covered by its protection system. I mean, this black structure. This is a system of tabs that can be opened and closed to protect the mirror from dust or moisture when the telescope is resting. Now, in the black tubular structure here, we have the secondary mirror. And the secondary mirror is the mirror in charge to concentrate the light collected by the primary mirror. So this light can be reflected again and can be sent to the main instrument. So you can see that the main mirror has a hole in the center. Okay, so the light has to pass through this hole to reach the instrument. So essentially, the primary mirror is a concave mirror. It's like a spoon. So the light from the stars is going to reach the primary mirror first. The light will be concentrated, will be reflected to the secondary mirror. The light will be reflected again down, so passing through this hole, and this light will reach the main instrument. Okay. Now, where's the instrument? Well, the harps, the instrument harps, is not visible here because it's completely isolated in another room, in another floor of this building. Okay. So the 360 started operations in 1977. At that time, it was a challenge for engineering, and it represented the big mission of ESO as an organization from its beginnings. The European astronomy was gathering forces from several countries to build an optical telescope in the 4-meter category, 4-meter class. This was the biggest and most advanced category at that time. Now, why it was so necessary to have a big telescope? Well, in astronomy, we analyze the astronomical objects through its light. The more light we collect, the more knowledge we can get. So in this case, if the mirror is bigger, we can collect more light, and in consequence, we have more information to analyze. So basically, you will be able to see fainter objects and to distinguish more, let's say, um, more, let's say, smaller details. Okay. Now, we have a short video to show you how this telescope is moving. So we are going to watch a very short. Okay, so this is the main telescope moving. So you can see that it's a big machine, but the movement has to be very, very precise. Now, a mirror for astronomy is not a normal mirror. Okay, it's not any mirror. The shape and the surface has to be perfect at the level of fractions of millimeters. Okay. Now, to achieve this in the 70s, let's say the ESO was able to to build an extremely thick mirror. The thickness in average is 53 centimeters. But this implies that the mirror is extremely heavy. So this mirror is 11 tons. Okay, this is the weight of the mirror, 11 tons. This is the equivalent of 2 African elephants. So if we want to build bigger telescopes, we need to find different solutions. So the next step was taken on the NTT, in the New Technology Telescope. So we are going to visit the New Technology Telescope later. Okay, so basically, this big telescope is a very important legacy of astronomy in the Atacama Desert. So we are going to visit in a few moments the next step, the evolution in terms of big telescopes in the 70s. Okay, so we are going to finish explanation here about the 3.6-meter telescope, and we are going out because we need to visit New Technology Telescope in a few moments. But before going to the New Technology Telescope, I don't know, Hector, if we have any question from our virtual visitors.
Okay, we have several comments. Most of them are greetings. Happy somebody is wishing just a good week. Saying that they can't wait for the tour. We have people watching us from Australia. So that's good. We have a Snowy here who happens to be his birthday. So happy birthday, Snowy. Have a wonderful day. And Snowy also has a comment here. He's saying that he will wish sometime to go to the observatory, and we actually have a in-process visit. So maybe you can talk about that a little bit.
Excuse me?
Yeah. So
Say again,
maybe you
please.
can tell Snowy and the rest of the people how can they visit the observatory.
Oh, yeah, sure. In order to visit La Silla or Paranal, because both observatories are open for visitors, you need to visit the ESO website, eso.org, and you will find a section about weekend public visits. Okay, so basically you need to do an online booking. I recommend to do it at least 2 weeks in advance because visits are available. Well, it depends on the season. A portion of the year is available Saturdays and Sundays, and other times is only on Sundays. But basically, you need to do an online booking, and you need to use your own vehicle from the closest big city. In this case, is La Serena, to reach La Silla, the entrance of La Silla. And from that point, there is a special bus to transport visitors to the main mountain top. Okay, and the visit is completely free, and you will have some tour guides in charge of doing the, um, the tour. This is only a daytime tour. It's only to contemplate, to visit the facilities, and this tour takes usually 2 hours, 2 hours and a half. So this is how you can do it. So as I told you already, the visit is free, but you need to get a vehicle to move from the closest city, La Serena, to La Silla entrance.
Thank you for it. Snowy also asked us if are we looking for life here in the observatory.
The instrument in the 3.6 meters, HARPS, is a highly specialized instrument to search for exoplanets. Okay, but this is an indirect method to find the exoplanets. This method is called radial velocity. Now, of course, we would love to find life, but this is not so easy. And the main mission of the HARPS instrument is just to detect the planet. Now, based on the on this first information, the detection of the planet, in some cases, it's possible to estimate the mass of the planet, the orbit, how close is or how distant is the planet from the central star. So in some cases, it's possible to estimate more or less if the planet is suitable for life. Okay, but this is very difficult to get a more accurate answer to that question. So that's why with the next generation of telescopes, for example, the ELT, um, right now under construction near Paranal, we expect to detect more specific things. For example, the chemical composition of the atmosphere of an exoplanet. So, again, this is not a definitive answer to the existence of life in another planet, but to be able to detect something so specific, of course, is a good step in the right direction. So essentially, yeah, of course, one of the main purpose of the science, astronomy, is, well, to try to find some kind of uh, planet that is suitable for life. But we are still working on it, and we need we need some more technology to be able to answer this kind of question.
Okay, we have another question here in Spanish. The technology right now allows to build larger telescopes, let's say 20 meters. What can we see there? And you already answered a little bit when you mentioned the ELT. Some,
Excuse me, there is a lag. Sorry.
let's see. Yes, so what can you tell about
Oh, you,
possible
you are asking
discoveries?
about this question, right?
Yeah. Well, you already mentioned that with a larger
Uh,
telescope, we could see the atmosphere of exoplanets and possibly find signatures of life. That would be one answer to this
yeah.
question.
So, for example, for example, when you have a larger mirror, okay, for example, with the next one, the ELT, yeah, one thing we can do is essentially to try to distinguish the chemical composition of the atmosphere of an exoplanet. Maybe some other things are a little bit more complex about. As far as I know, there are some plans to do a better characterization of the dark matter. Uh, um, I mean, when you are analyzing galaxies, maybe to detect some specific objects that are too far away, and, and they are extremely faint. I mean, things that are not exactly possible right now with our current mirrors. Now, um, in some cases, when you have a larger mirror, I mean, like the ELT, you can get a better insight of, for example, star forming regions, okay, nebulas. So maybe you can understand better how new stars um, are rising in other parts of the universe. So I don't know, Hector, if maybe you have more insights about
Yeah, like another thing
future
that you could
plans of the
do,
ELT, for example.
yeah, you could also try to look for objects that
Mm.
are very faint because they're very far away. So you could go into the look for the first galaxies and the
Mhm.
first generation of stars. That's something that definitely going to be more possible with ELT than with our current technology. And already with James Webb, we
Yes.
went even farther than we already believed we are going to find things. So with DLT, it's probably we are going to go even farther than that. Okay, we have 2 more questions before we continue with the tour. So Sharif is asking about images of 3E Atlas. Where can we expect some of them?
Well, as far as I know right now, this object is like going out from the perihelion, right? Perihelion, right?
Yeah,
So, so probably in the upcoming days, it will be possible to get more high definition pictures. But I don't think that the ESO telescopes are working on that, or maybe there is some kind of future campaign
yeah.
to do that. But I know that there are some space telescopes and space probes trying to do that because they are
Mhm.
more or less near that object in the space. But I don't know if some telescopes are
I
trying to do that.
read somewhere that they were going to do some observations with Gemini telescope, but I haven't.
Gemini South, right?
Yeah,
Oh, okay, okay. Yeah, but in any case, I think we need to wait a few more days, right? Because right now
yeah.
it's
Like
too
right now
close
to be like behind the
of the
sun,
sun.
so we cannot. Yeah, and
Yeah,
the
it's,
last.
it's behind the sun, so it's impossible to take a picture right now. Yeah, so we need to wait a few more
Mhm.
days. Exactly.
Okay, and Marcin is asking us if we can use entity for observe comets and comets research.
Well, yeah, technically, yes. You can observe comets. You can observe asteroids. The thing is that, for example, big telescopes such as the La Silla, NTT, Paranal, yeah, they can observe asteroids. The thing is that you need to present some kind of project, a scientific project, and you need to justify why you want to observe that. And if you have a good reason to do that and you have enough scientific merit to observe that, yeah, you can get some telescope time. Um, you can even point to some planets if necessary. But the thing is that you need a very good project because you have a lot of people wanting to observe in this kind of big telescopes, and you have a lot of different projects that need to be analyzed. Okay, so as long as your project has enough scientific justification, yeah, essentially you can do it. And when you are observing a comet, for example, or an asteroid, the only adjustment you need to do is to adjust the rate of the movement of the telescope because the motion of a comet of an asteroid is not the same, let's say, rate of the stars because of the rotation of the planet. Okay, all stars appear to move at a certain rate, but asteroids are comets, and comets, they have a different rate of motion. Okay, so this is the only adjustment, but essentially, yeah, you can observe comets or asteroids if you have a good reason to do that.
Okay, I think we can continue with the tour for now, and we can have a second round for more questions later.
Yeah, sure. Okay, so we are going to proceed with the visit of the NTT. We are going to visit a new telescope here because the NTT is an acronym of New Technology Telescope. Okay, so basically, we have some differences between the NTT and the 3.6 meters. Now, the mirror of the NTT is essentially very similar to the 3.6-meter telescope. Okay, but we have some important differences in the facilities here. For example, the NTT was inaugurated in 1989, and And the dome, maybe in this picture is possible to see, in this dome we have a system of flaps. Okay, so this represented an evolutionary leap in the construction of telescopes, because it was possible to host instruments in smaller, lightweight structures and more efficient facilities in terms of the circulation of the air in the interior. So basically, if you look at this dome, this looks very different if we compare to the classical spherical dome, like the 360. Now, when I was talking about the flaps or this kind of little, let's say, windows here, basically this is important because the air can circulate without too many obstacles. So this can help to reduce the possibility of turbulence, preserving the sharpness of the pictures. Okay, so if you remember the big structure of the 360, in this case this building is smaller, and if we look at the telescope, we can estimate that a person, for example, is the size of this door. Okay, so the difference is not too big. Okay, and you remember in the 360 the telescope is huge, is a super huge telescope compared to a person, for example. But in this case the telescope is more compact. So as you can see here. Now the other important thing is that the building is attached to the telescope. So essentially, the mounting of the telescope is totally different. So when the telescope wants to rotate, all this building needs to rotate, because all this portion of the building is attached to the telescope. So all of this is acting like the structure, providing the rotation. Okay, so again, when the telescope needs to rotate, all this dome needs to rotate as well. Now, if we look at the mirror here, I am going to do a close-up. We can see the main mirror here. This disc here is the mirror, and we can see that there is a little bit of light reflected. Now, if you remember, the 360 or the 3.6 meter telescope has a mirror with 53 centimeters thickness. In this case, the mirror of the NTT, well, first is almost the same diameter, and in this case is 3.58 centimeters. Okay, sorry, 3 meters and 58 centimeters. Okay, and this mirror is thinner. The thickness of this mirror is only 24 centimeters, and is a more light mirror, because in this case the weight is only 6 tons. So this is the equivalent of one African elephant. Okay, we can see something additional here. This mirror is concave. Okay, it's like a spoon. Same like the 3.6 meters. Now, the thing is that when the mirror, when the telescope is pointing to a different object in the sky, we need to rotate the mirror. We need to put the mirror in a different position. So, because the mirror is so heavy, when the mirror is when the telescope is inclined, the mirror can suffer distortions in the concave shape. So we need to do something to compensate this distortion in the concave shape. So in this case, next to the mirror, let's say below the mirror, here, we have something. We have a system of actuators this is a kind of pistons, okay? They are not visible because they are covered by this structure, but basically we have 75 actuators, and the actuators are basically providing a small pressure, okay, to the mirror. So in this case, we can compensate any distortion in the concave shape to preserve the concave shape all the time. So we control this system with a computer, and we call this system active optics. The active optics system was developed by ESO, and this was a technological advancement fundamental for the construction of the next generation of telescopes of the 10-meter category. Today, we are using this technology in all modern telescopes. For example, in the Very Large Telescope, or VLT, in Paranal Observatory, and in the future in the Extremely Large Telescope, or ELT, that right now is under construction near Paranal. Now, maybe you are asking, maybe you are wondering, where is the people? Where are the scientists? Where are the astronomers at night? Well, they are not here. They are not inside of the telescopes. They are in another separate location. They are in a control room, a dedicated control room, and basically they are working from there all night, and they are doing a remote control of the telescopes from the control room. So we have a short video to show you what happens in the control room at night. So in this time lapse, we can see a couple of workstations. The workstation to the left is for the entity, and the workstation to the right is for the 3.6 meter telescope. So you can see some people working there. We have a few astronomers, we have telescope operators. We don't need a lot of people working there, but basically they are working in some kind of office space, office environment, and they need to work there all night. Okay, so this is basically what happens in the control room of La Silla. Okay. So, well, right now you know already a lot about the observatory and the people working here. But now I want to invite you to take a look at the main scientific milestones made from all ESO observatories. I mean La Silla, Paranal, and Chajnantor. Okay, so astronomers from all the planet are using the telescopes to study objects close to our home, our solar system, but also others located in the most distant places in the universe. So please pay attention, because now we are going to present the most important scientific milestones.
Observations with ESO telescopes have led to many breakthroughs in astronomy, and over the years have been responsible for some truly remarkable findings. Here is our list of ESO's top 10 astronomical discoveries so far. Astronomers using ESO's Very Large Telescope have discovered by far the brightest galaxy yet found in the early universe, and found strong evidence that examples of the first generation of stars lurk within it, stars that were previously only theoretical. These massive, brilliant objects were the creators of the first heavy elements in history, elements that are necessary to forge the stars we see around us today, the planets that orbit them, and life as we know it. ESO telescopes have provided definitive proof that long gamma-ray bursts are linked with the climatic explosions of massive stars, therefore solving an enduring mystery. A telescope at La Silla was also able to observe the visible light from a short gamma-ray burst for the first time, showing that this family of objects most likely originates from colliding neutron stars. Astronomers using ESO's HARPS instrument in 2010 discovered a planetary system containing at least 5 planets orbiting the Sun-like star HD 10180. They also found evidence that 2 other planets may be present, one of which, if confirmed, would be among the lowest mass exoplanets ever found. Newer observations and reanalysis of the data suggest that there could be even more planets around this star. ESO's Very Large Telescope was used to detect carbon monoxide molecules in a remote galaxy, seen as it was 11 billion years ago, a feat that had remained elusive for 25 years. This allowed astronomers to obtain the most precise measurement of the cosmic temperature at such a remote epoch, and it matched the temperature predicted by the Big Bang theory. The atmosphere around a super-Earth exoplanet was analysed for the first time using the VLT. The planet, which is known as GJ1214b, was studied as it passed in front of its parent star, and some of the starlight filtered through the planet's atmosphere. The atmosphere was found to be either mostly water in the form of steam, or dominated by thick clouds or haze. Using ESO's VLT, astronomers measured the age of the oldest star known in the Milky Way. At 13.2 billion years old, the star was born in the earliest era of star formation in the universe. Uranium was also detected in a Milky Way star and used as an independent estimate of the age of the galaxy. The VLT obtained the first ever image of a planet outside our solar system. The planet, which has a mass about 5 times that of Jupiter, orbits a failed star, a brown dwarf, at a distance of 55 times the average distance between the Earth and the Sun. In 2014, ALMA, the Atacama Large Millimeter Submillimeter Array, revealed remarkable details of a solar system that is forming. The images of HL Tauri were the sharpest ever made at sub-millimeter wavelengths. They show how forming planets are vacuuming up dust and gas in a protoplanetary disk. One of ESO's proudest moments came when 2 independent research teams, including ESO staff, arrived at a truly revolutionary finding: that the cosmos is not only expanding, but that it is doing so at an increasing rate. The findings of the separate teams were based on observations of exploding stars, or supernovae, including measurements made from ESO's telescopes at La Silla and Paranal. This discovery was rewarded with the 2011 Nobel Prize in Physics. And finally, several of ESO's flagship telescopes were used in a 20-year study to obtain the most detailed view ever of the surroundings of the monster lurking at the heart of our galaxy, a supermassive black hole. Astronomy is always moving forwards, and ESO's top 10 scientific discoveries are not set in stone.
Okay, so that was the top 10 scientific milestones, but we have one extra result, something like a bonus track. We are going to visit that quickly. A team of astronomers was able to capture the first picture of a black hole. The Event Horizon Telescope, or EHT, an array of 8 ground-based telescopes distributed on the planet, thanks to an international collaboration, was able to achieve the first visual direct evidence of a supermassive black hole. So the picture in a few moments will reveal the black hole in the center of Messier 87. This is a massive galaxy in the nearby galaxy cluster of Virgo. This black hole is located 55 million light years from Earth, and it has a mass of 6,500 million times the mass of the Sun. Okay, so this was the top 10. And now we are going to do a very, very special activity because this is not possible during a public visit in La Silla. We are going to explore La Silla at night. So you can see in this picture, in this 360 panorama, a typical starry night from La Silla. So in this picture, we have the entity here. This is the dome of the entity. And we have some important astronomical objects and regions. So, for example, we have a very popular constellation here next to the horizon. This one right here. This is called Orion. This is the constellation Orion. This one is visible from the northern and southern hemisphere. And here we can see those three stars somewhat aligned, representing Orion's belt, because Orion in the mythology is a hunter. So these three stars align here, they are representing Orion's belt. Okay, and next to this area we have something here. This is the Great Orion's Nebula. This is basically a star-forming region in Orion, and it's very, very bright. Actually, you can see this nebula with your naked eye, like a bright spot in Orion's constellation. And you can also detect this nebula with binoculars or even a small telescope. So it's a very, very interesting object for amateur astronomers and professional astronomers as well. Okay, so if we continue moving here, we can see something here up in the sky. This star is the brightest star in the sky. This star is called Sirius. Sirius is part of another constellation called Canis Major. Canis Major is representing one of the hunting dogs of Orion. So basically, we can say that Sirius, the constellation of Sirius, is connected in the mythology to Orion. Now, if we look at this area in perspective, you can see that there is more concentration of stars here, right? So we have more stars here if we compare with this area or this area. This is because all of this path of light and dust is one of the arms of the Milky Way, our galaxy. So in a clear night like this one, we can see one of the arms of the Milky Way. And of course, this area is very populated with stars, nebulas, dust. So it's a very beautiful portion of the sky. Now, if we look again to the horizon, but we change the perspective, I am going to show you the south cardinal point, because if we look toward this direction, you will find two spots in the sky, those ones. Those spots are the Magellanic Clouds. The Magellanic Clouds are galaxies. They are irregular galaxies, and they are also satellite galaxies of the Milky Way. Now, those objects are visible only from the southern hemisphere. So, amateur astronomers, for example, from Europe, they like to come to the Atacama Desert because they cannot look at those objects from Europe. You need to you need to be at the southern hemisphere to see those objects. The name Magellanic Clouds is because of the records of Ferdinand Magellan during its circumnavigation of the planet in the 16th century. I mean, a time when no one was aware what a galaxy is. Okay? So these are the Magellanic Clouds. And next to this area, we have the smallest constellation in the sky. This is the Southern Cross right here. this is the smallest constellation of the 88 official constellations in the sky. Now, the Southern Cross is also useful because if you project the longer stick of the Southern Cross, I mean this one, 4 times and a half, you will find a point in the sky that is called the South the South Celestial Pole. The South Celestial Pole is basically the projection of the of the geographical South Pole. So basically, if you try to take an astrophotography pointing to the South Celestial Pole, you will get this kind of concentric circles. Okay, the typical circles that you sometimes maybe can see in some astrophotographies. Now, as I told you already, if you project this longer stick, you need to do it 4 times and a half. So I am going to do it. We'll project 1, 2, 3, 4 and a half, and more or less like here, you would have the South Celestial Pole. Now, you can also get the same if you try to do something like a triangle with the Magellanic Clouds. Okay, so you have 2 ways actually to do it. And if you look at the horizon from this point, if you look at the horizon, you are actually looking at the south cardinal point. Okay. Now, and the last thing I want to show you from here is from this view, we have the 3.6 meter telescope, and just behind of the telescope we have the center of the Milky Way rising about the horizon. So, of course, the center of the Milky Way is a beautiful area because it's very populated with stars, with dust, with nebulas, with deep sky objects. We have a lot of things here. In this picture, for example, you have the Antares star from Scorpius. So this is a very beautiful area, and something very interesting about the southern hemisphere is that in winter months, the southern hemisphere, I mean May, June, July, you can you can observe the center of the Milky Way just about you. So you can see all the Milky Way from the southern hemisphere all night. This is a big difference if you compare with the northern hemisphere, because I know that in the northern hemisphere you cannot see all the Milky Way. You can see something like I don't know, maybe 70% of something like that, and closer to the horizon. But here in winter months, May, June, July, you can look at the center of the Milky Way all night about you, and I will I will show you that in the last picture of this virtual tour. Okay, so in order to finish this virtual experience, I am going to show you something else. This is the 3.6 meter telescope from the mountaintop. This glare there is light pollution from La Serena. Well, you need to keep in mind that light pollution is a big problem for astronomy in general. So we need to keep the light pollution under control. Okay, so of course we don't want to increase this light pollution, and that's why we have some legal regulations in the north of Chile to avoid light pollution to affect astronomical observatories. And from this picture, we can see in the distance the telescopes there, and we are going to move because I want to show you this is the road connecting all the telescopes, all La Silla telescopes at night. So this road eventually will also finish in La Silla Hotel. So this place will be the end of our visit, because this place is basically a very nice location for the staff, because basically you have the dormitories, you have the restaurant, you have all the necessary facilities for the astronomers, for the scientists, for the engineers, so they can rest and eat and spend time here when they are not working. This person here is the photographer in charge of all the pictures of this virtual experience, and this picture was taken during winter months in the southern hemisphere. So I want to finish this tour with this beautiful picture, because here you can see the center of the Milky Way just above you. So this is an impressive view, and this is why many people, amateur astronomers, astrophotographers, they love to come there to the Atacama Desert to take a look and take pictures of this beautiful area in the sky. Okay, Hector, I don't know if we have time for one last pictures before we finish the reporter.
Okay, let's go with one of the last questions. Here, you have a question about protections against earthquakes in the observatory.
Oh yeah, well, for example, regarding the NTT, well, we have some protections. Okay, so for example, there is a massive concrete foundation, something like a column, a big pier. So basically, the telescope sits on a separate concrete pier. So basically, this pier is structurally isolated from the dome and walls. So basically, the vibrations from the dome, I mean, by wind, human movement, or even earthquakes, don't transfer to the telescope. So that's important. And this is a regular practice when you are building new telescopes, to isolate the telescope from the rest. Okay, and also the azimuth mounting and the compact structure, they were designed to minimize resonance and distribute the stress evenly during tremors or earthquakes. So this is usually what happens about earthquakes.
Okay, and with that, I think we are on time to end today's tour. So for my side, I say goodbye to all of you, and please keep an eye for when the next tour is going to be, in which language we are switching between Spanish and English, and between the Silla Observatory and Paranormal Observatory.
Okay, thank you very much, Hector. So yeah, you please remember that all these visits, informations, and pictures, etc., is available on the ESO website. And from my side, yeah, I want to say thank you very much. Please stay alert to the ESO social networks to know when will be the next virtual tour, Paraná or La Silla, English or Spanish. So thank you very much. And on behalf of ESO, I want to say thank you very much to everyone for your presence. So thank you and goodbye.